First of all, I'd like to thank Jeff for his feedbacks to my first teaching segment. About the points he mentioned there, first is that yes, the sound levels were a problem. Actually, the screen recording software that I used to record the whole thing gave the overall sound levels quite low, so I had to actually magnify the voice levels, the sound levels, and thus the background noises also got amplified. And to bypass this problem, this time I'm doing an audio segment. And about the technical things, yes, I need to work upon the pronunciations of some words to make them easily understandable. And also, yes, I do need to slow down a little bit so that things can be easy to follow. So I guess I'll start. This time I'll be talking about something called the pigeonhole principle. It's actually nothing fancy, it's quite intuitive, but it is one of the most widely used tools in discrete mathematics and combinatorics, and it is widely applied in real life problems. We'll see how, but first of all, let me tell you that what it is. So suppose there is an old house, old decrepit house, and there are holes in its walls, and some pigeons live in these holes. And of course, if there are more pigeons than the holes, then there must be a hole in which two or more pigeons live. In a sense, this is the pigeonhole principle, and it is formalized like this: if k plus 1 pigeons are placed into k pigeonholes, then at least one pigeonhole will contain two or more pigeons. And now let's move on to a couple of examples to explain its usefulness and how it can be used to solve problems in the real life. In the first example, it says that a manufacturer of computers makes at least one PC every day over a period of 30 days. He makes at most 45 computers in this period, and if he starts making a computer on a single day, on a given day, he finishes his job. And we have to show that there must be a period of consecutive days during which exactly 14 computers are made. And to show how pigeonhole principle can be used to solve this problem, let's first define that AI be the number of computers made from the first day to the ith day. So the number of computers made in the day 1 is A1, day 2 is A2, and up to number of computers made from day 1 up to day 30 is A30. And of course, as at least one computer is made in a single day, A1 is less than A2 is less than up to A30, and A1 is greater than equal to 1, and A30 is less than equal to 45, because the total number of computers made in the 30 days is at most 45. And now we add 14 to each of these numbers, so that A1 plus 14 is less than A2 plus 14, up to A29 plus 14 is less than A30 plus 14. And since A30 is less than equal to 45, A30 plus 14 is less than equal to 45 plus 14, which is equal to 59. Now is the interesting thing. We have that A1 is less than A2 is less than A30, which is less than equal to 45, and this is less than 59. And also we have A1 plus 14 is less than A2 plus 14 is less than A30 plus 14, which is also less than equal to 59. So we have 60 numbers, A1 up to A30, and also A1 plus 14 up to A30 plus 14. All of these are less than equal to 59. So now comes the application of pigeonhole principle. If say we substitute numbers with pigeons, so there are 60 pigeons, and the total possible numbers are 59, and we substitute these with holes, so the number of holes is 59. So there are 60 pigeons and 59 holes, so there must be a hole where two pigeons live. So there must be a number for which two of these numbers are equal, and they cannot be from the same set because a1 is less than up to a1 is less than a2 is less than a30, and a1 plus 14 is less than a2 plus 14 up to a30 plus 14. So there must be two numbers, one from each of these sets, such that ai is equal to aj plus 30, and thus we have that ai minus aj is 14, which means that exactly 14 computers are manufactured between the ith and jth day. Cool, right? So that's one of the applications, one of the easy applications of pigeonhole principles. And now we move on to our second problem. This problem says that assume that among 6 persons, each pair of persons are either friends or enemies. Then either there are 3 persons who are mutual friends or 3 persons who are mutual enemies. That's what we have to prove. Now say there are 6 persons, and let A be one of these persons. Take any of them, these 6 persons. So there are 5 more persons, and by the pigeonhole principle, of these remaining 5 people, either 3 or more of them are his friends or enemies, or there are 3 or more of these people are enemies of A. So without loss of generality, say 3 of these are the friends of A, and they are B, C, and D. So, and we consider now these 3 persons, B, C, and D. Among these 3 persons, B, C, and D, there are connections B, C. There are 3 connections actually, B, C, C, D, and B, D. Now, if any of these 2 persons are friends among themselves, then these 2 persons and A, they are mutual friends because both of them are friends to A. And if not, if all B, C, and D, these 3 peoples are enemies of themselves, if all pairs of these people are enemies, then we have 3 people who are mutual enemies. So either we have 3 mutual friends or we have 3 mutual enemies, and we prove whatever was needed. And this was done by pigeonhole principle, mind it. So there are varied applications of this thing. And also there is one interesting thing, is that from this problem was actually an introductory theorem of a topic in number theory that is called Ramsey numbers.